complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born like this from the death of a star, its diameter is 50 kilometers at most. But one can find black holes of truly monstrous proportions, over 10 billion kilometers in diameter. Andrea Ghez is an expert on this invisible phenomenon of the black hole. It was when she saw the Apollo moon landing on TV that her interest in space was awakened.
My biggest objective in life when I was very young was to become a ballerina. So I think I see things spinning in space now as opposed to myself. But yeah, your path the path was unclear. And today I view doing astronomy and studying the black hole as putting together one big puzzle.
Donald Lyndon Bell predicted that a supermassive black hole lurks at the heart of every galaxy. Andrea Ghez tried to find such a black hole in our own Milky Way galaxy.
Actually, the first thing that we're trying to do is watch how stars move. That's the key to finding that there's a black hole. And the way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Ghez followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Ghez used one of the observatories on this summit, the Keck Observatory. The Keck has 2 of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Gelessen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours, so we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star, which people were very excited about in the earliest days, was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is 4 million times the mass of the Sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered this natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度を見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and congratulate you on your great discovery." The letter came from England. The sender? None other than Donald Lyndon Bell, who had predicted the existence of supermassive black holes.
I was very happy because I didn't feel that I absolutely knew. I thought it was likely, and gradually I thought it was more and more likely.
A black hole equivalent to 39 million solar masses was sucking in huge volumes of gas with its tremendous gravitational force. The dark object in the center of this artist's conception is a black hole. Its diameter is awesome, as if 160 of our suns were lined up in a row. It is now thought that almost all galaxies have these supermassive black holes at their center. The most advanced observational instruments are detecting ever larger black holes. Situated outside Earth's atmosphere, the Hubble Space Telescope can see space objects with great clarity. Hubble took aim at NGC 7052, a galaxy located 37 million light-years away. The image it captured was that of a huge disk, comprised of gases and stars. In its center, there ought to be a supermassive black hole.
When we got this image, I was just super excited, because it was such beautiful, rich detail that I really knew right when I saw this that we were going to be able to get, excellent spectra and really be able to determine whether this galaxy has a black hole and how massive it is. So I was very, very excited.
The galaxy was indeed harboring a supermassive black hole. A black hole equivalent to 300 million solar masses. That's more than 70 times larger than the one at the center of our own Milky Way galaxy. A black hole with the diameter of 1,200 of our suns lined up in a row. And Hubble has spotted an even larger one, an ultramassive black hole. This one is in M87, 59 million light-years away. Scientists had long been puzzled by a band of white light there. When Hubble was trained on the galaxy's core, the band of white light was revealed to be a gigantic jet of gases. As the gases are sucked violently into the black hole, a portion of them are ejected in the form of this jet. The mass of the black hole at the base of this jet has been calculated to be 6.4 billion solar masses. That's 10 million times greater than the supermassive black hole at the center of our Milky Way galaxy. In size, its diameter is equal to 25,000 of our suns lined up in a row. Then, in 2011, the largest black hole in history was discovered. In the galactic nucleus of NGC 4889, there's an unimaginably monstrous black hole, with a mass equivalent to 9.7 billion times that of our sun. What scientists are most eager to elucidate now is the process by which these black holes become so large. They may start with the death of a star, but how do they then grow to billions of times their original size? Trinity College at the University of Cambridge. Isaac Newton, who formulated the universal law of gravitation, conducted research here. Martin Rees has served as Master of Trinity College. Rees has conducted research on supermassive black holes together with Lyndon Bell. The impetus for his research was the discovery of galaxies whose high-energy cores were emitting powerful radio waves.
Well, there were various alternative theories about what might be happening in the centers of the galaxies, which are putting out a concentrated high source of power. And these ideas included a very dense cluster of stars, a very massive star, a binary supermassive object, etc. And I realized that if you followed forward the likely evolution of any of these objects, they would all have no alternative to becoming a big black hole.
So any object emitting sufficiently high amounts of energy will inevitably become a supermassive black hole. How then are supermassive black holes born? The Rees diagram, as it was called, charted the possible routes.
If you're going to be at that, you need to have...
In the 30 years since the Rees diagram was published, there has been a succession of discoveries of supermassive black holes. At the same time, the study of their birth has also been progressing. One scenario suggested by Rees was the consolidation of several smaller black holes. At the end of their lives, stars explode, forming relatively small black holes. Hundreds of millions of them may cluster together, merging into one supermassive black hole. This is NASA's space-based Chandra X-ray Observatory. Chandra has been examining a region where black hole consolidation is thought to be taking place. Galaxy NGC 6240 is located 400 million light-years from Earth. Actually, two galaxies are colliding there. As Chandra examines their galactic cores, two bluish-white spots appear. They are both massive black holes, one at the center of each galaxy.
This blue region here is a blow-up of the center, and you can see there are two little sources there, one brighter and one a bit fainter. But each of those, when we look at the spectrum, shows a very characteristic sign that this is just emission from a supermassive black hole in each case, which has never been seen before until we had the beautiful Chandra image and could separate the two.
Two black holes in close proximity to each other, but they cannot soon merge. Rather like the Earth and the Moon in their perpetual dance, the two black holes orbit about each other without colliding. So what about Rees's concept of black holes merging to form a supermassive black hole? Masayuki Umemura uses a supercomputer to create simulations of black hole mergers. Here, he simulates the behaviors of 10 black holes of equivalent mass. The first consolidation happens far sooner than expected. It takes only 50 million years. The process repeats. Within about 500 million years, 5 black holes have merged into one.
もともと銀河が持っていたブラックホールが、大きな銀河に取り込まれたときにブラックホールごと、中に取り込まれるわけですね。そうすると2つではなくて、例えば大きな銀河の中に10個のブラックホールがあるというような状況が最初に起こった可能性が高いということをまず想定しました。
Let's look at our actual universe. There are galactic collisions and mergers all over the place. And when galaxies merge, the thinking is that their black holes merge too. Wherever galaxies cluster, there's bound to be a cluster of black holes. That means a process of consolidation of black holes. This conforms to actual observations of our universe. A second Reese diagram scenario has a seed black hole becoming supermassive by swallowing up gases and stars. In that scenario, the monster is born by gulping down an unbelievable quantity of gases, equivalent to hundreds of millions of our sun. The gases are sucked in with so much force that the friction produces incredible heat. That violent process emits intense light and X-radiation and blows away surrounding gases. The result is that there are no more gases to feed on, and the black hole ceases to grow. But how is it that such a huge quantity of gases could be sucked in the first place? Gases that are being sucked in, blowing away other gases. Ken Osuga studies this contradiction. He has found a particular mechanism within black holes by which they can continue to draw in vast amounts of gases. He's prepared a simulation of one scenario for how supermassive black holes may be created. As a black hole sucks in gases, it generates magnetic field lines, which penetrate the surrounding gas disk like hoops. Thus embedded, they are then distorted by the swirl of the disk. As the disk swirls, the magnetic field lines are caught in a spiral vortex, twisted and coiled like a spring. This is a plasma jet. A portion of the disk's gases, charged with energy such as light, shoots out in opposite directions perpendicular to the disk. Any remaining gases are sucked into the black hole, which grows supermassive.
私たちの研究の結果はですね、光の力が非常に強くなったとしても、ジェットは噴出するけども、ガス円盤からガスは変わらず吸い込まれ続けるということを明らかにしました。これによってですね、ブラックホールは大量のガスを吸い込むことができますので、巨大ブラックホールに成長するのに一役買うということを証明することができました。
Hubble has captured this actual image of an intense jet erupting from the center of a galaxy. The gas-guzzling scenario for supermassive black hole creation, as outlined in the Reese diagram, thus seems persuasive. Martin Reese developed several theories of supermassive black hole formation. One was by the continuing consumption of gases. Another was by the consolidation of smaller black holes. But the Reese diagram indicated a third possibility as well. Under this third scenario, just after the creation of the universe, large clouds of gas condensed into supermassive black holes directly, without first becoming stars at all. Recently, evidence for this third scenario has also come to light. By combining information from the Chandra X-ray and Hubble Space Telescopes, Priya Natarajan hunts for supermassive black holes created at the inception of the universe. These far-off galaxies were photographed by Hubble. Among those circled on the screen are some that are 12 billion light-years away. They are small galaxies, born immediately after the universe itself. Some 200 of them have been identified. Here's one as perceived by Chandra. And it already has a supermassive black hole in it. Natarajan was surprised to discover that almost all 200 of them had supermassive black holes in them. If so many supermassive black holes were already present immediately after the creation of the universe, then that lends powerful support to the third scenario in the Reese diagram.
So just as we think that a gas cloud that is collapsing could make the first star reasonably easily, the conditions that you need for making a black hole seed directly without forming a star, instead of forming a star, also exist in the early universe.
Efforts are also underway to confirm the third Reese diagram scenario computationally.
I think it is the first time that there is a model showing that it is possible to produce a precursor of a big black hole in the form of this supermassive black hole.
This is a giant gas cloud, 100 light years in diameter. 70,000 years after it formed into a gas cloud, its gases were compressed into a disk 1 light year across. The gas disk was equivalent in mass to 100,000 of our suns. It then condensed further, compressed by its own weight, giving rise to a supermassive black hole. So the third scenario in the Reese diagram, going directly from gas cloud to black hole, is a real possibility. Studies of the origins of these supermassive black holes are ongoing. The latest research reveals that the supermassive black holes do not simply grow fat, consuming everything nearby. Surprisingly, they exert a huge constructive effect on the space around them. What these remarkable monsters call home is a galaxy's core. More specifically, it's inside the concentration of stars called the bulge. The shape and size of the bulge varies with each galaxy. John Cormandy has investigated the relationship between the mass of a bulge and of its supermassive black hole. The first galaxy he observed was Andromeda. The supermassive black hole here is equivalent to 150 million solar masses. The bulge is approximately 1,000 times greater in mass. Next, he looked at the Sombrero galaxy. The black hole here is 1 billion solar masses. The mass of the bulge is approximately 1,000 times that. Plotted on a graph coordinating the masses of the bulges with those of the black holes, the galaxies form a nearly straight line. In most galaxies, the black hole to bulge ratio of masses is 1 to 1,000. This strong relationship between the mass of supermassive black holes and their galaxies' bulges surprised many scientists.
We know that when gas densities get very big, you get a burst of new stars being formed. And so at the same time when this burst of stars is making the bulge, the rest of the gas is being fed to the black hole and making the black hole bigger. So you get lots of new stars, and you get higher mass black hole, and the two correlate.
A galaxy comprises hundreds of billions of stars. It turns out that at the galactic cores, the black holes and the bulges have a deep interrelationship. A giant bulge will correlate with a giant black hole, a small bulge with a small black hole. This strange law of outer space may mean that galaxies and black holes evolved together. Andrea Ghez discovered the supermassive black hole at the center of our own Milky Way galaxy. She also found evidence that it performs an astonishing function within the galaxy's bulge.
We've had one surprise after another in our study of the center of the galaxy. What we see is that they're very massive stars, which tells us that they're very young stars. And the last thing you expect near a black hole is to find a very young star, because black holes are very inhospitable to star formation. They should just tear apart any cloud that might eventually become a star. So you really don't expect to see young stars, baby stars near a black hole. And yet all the stars that told us that there's a black hole are the ones we predicted shouldn't be there. So it's one mystery after another.
Near the supermassive black hole at the center of the Milky Way, Ghez found many baby stars. This suggests something astounding, that new stars may be emerging from the gases that originally accumulate around a black hole. The effect black holes have on surrounding space is not limited to the birthing of stars. A project spearheaded by NASA called death.A is endeavoring to capture distant galaxies. death.A involves the participation of radio telescopes in a dozen locations in the southern hemisphere, chiefly in Australia, but also in Chile, South Africa, and the South Pole. One of its targets is a galaxy located 14 million light-years from Earth, Centaurus A. This is the image they obtained, a clear view of a plasma jet violently shooting out from an invisible black hole. The jet bursts out at 30% of the speed of light. Analysis of this jet turned up something quite unexpected. The jet shooting out of the black hole even escapes the galaxy itself. Its plume expands for a distance of 1 million light-years. So the black hole doesn't just guzzle down gases, it sends out the stuff that stars are made of far beyond its own galaxy. The role of the supermassive black holes in the universe is still largely mysterious, but scientists are learning more and more.
Cosmos looks the same from Britain and from Japan. Indeed, the night sky is the same to all of us and has been the same to all our ancestors throughout human history. It's the one common feature of all humanity. They've all looked up at the night sky and wondered at it and interpreted it in their own way. It's a wonderful story where we found all these extraordinary objects in the universe, and we can understand these vast cosmic horizons in a way that our ancestors could only have dreamed of. So it's a wonderful story.
Supermassive black holes, monsters in the galactic cores. They may gobble up everything around them, but they also give birth to stars and send out energy-rich materials into the universe. Some came into being at the same time as their galaxies and grew along with them. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度を見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and
4 million times the mass of the Sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered this natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. Shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star which people were very excited about in the earliest days was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is...
The way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Gez followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light-years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Gez used one of the observatories on this summit, the Keck Observatory. The Keck has two of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Gillesen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours. So we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002. The European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine. The black hole is a bizarre space object, defined by the absence of everything except gravitational force. How do scientists wrap their minds around it? It's complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born,
from the drama of our planet's origins and the birth of our solar system comes one of the most startling revelations of modern science. The solar system we see today, quiet, stable, was once a battlefield. Newborn planets blasted through space, competing for stable, circularized orbits inside a grunge-style mosh pit of gas and dust. For those that find the right balance, the prize is survival. For the rest, world-shattering destruction. A new look at the chaos of creation and a frightening possibility in our distant future. Mars. The Curiosity rover is searching for clues about the origins of the red planet. It confirms the presence of oxygen and nitrogen isotopes hidden in the rocks and soil.
We use isotopes to try to figure out the history of planets, partly because they are immune to many of the changes, the chemical changes that occur when you have things like collisions and so forth. Isotopes, the relative abundances of these isotopes are like fingerprints.
Curiosity confirms a unique mix of isotope fingerprints. The isotopes indicate that Mars formed elsewhere in the solar system and moved into our neighborhood. Our solar system is full of oddities pointing to an imperfect birth and a malformed evolution. All of our planets go around the sun in the same direction that the sun is spinning. This is the same direction that the clouds within our original nebula began to rotate. 6 planets spin around their poles in the same direction. For them, the sun rises in the east and sets in the west. Yet 2 planets spin the opposite direction. For Venus and Uranus, the sun rises in the west and sets in the east. Uranus not only has a retrograde spin, it rolls on its side like a bowling ball. At Neptune, the icy moon Triton orbits backwards, opposite from the direction of Neptune's spin. Do these planets spin backwards because they were rocked by titanic collisions in the past?
So we see evidence in the architecture of the solar system for not only collisions like Earth's moon and the fact that Venus is rotating in the wrong direction and Uranus is on its side and so forth. All these things are attributed to collisions. We also see in the asteroid belt and in the Kuiper belt, the outer asteroid belt if you like, we see that the orbits of these things look like they've been disturbed.
Closer to home, our own Earth has an inexplicable 23.5-degree tilt. Its spin axis is radically misaligned from its magnetic pole. And our moon is comparatively large for a planet our size. Now, a new theory may be able to explain many of these oddities. It is called the Grand Tack hypothesis. Four and a half to 5 billion years ago, a gas giant planet arose inside a primordial disk of gas and dust.
Jupiter didn't just form where it is, but formed and then moved inward towards the sun.
As it spirals toward the sun, Jupiter herds asteroids and rubble.
Jupiter's natural tendency is to drift in slowly through this debris field that it's traveling around.
The inner solar system is also thick with gas and dust. The birth of our planetary system is well underway. Numerous worlds are born in this region, including the Earth. Primordial skies are ruled by chaos. Jupiter's approach destabilizes these planets. Their orbits decay into wildly swinging ellipses. Some are tossed out. Others fall into the sun. Their numbers are unknowable. These are ghost worlds from a bygone age.
Jupiter just causes all heck to break out in the solar system, and all that debris in the outer solar system gets flung inward towards the inner solar system.
And it was a busy time in the very early solar system, and things were colliding with each other all the time.
And then it stopped. Jupiter's invasion of the inner solar system is mysteriously halted. The planet makes a turn, or, in sailors' parlance, a grand tack. Lurking behind Jupiter is a second gas giant, Saturn.
So as Jupiter was migrating inward, Saturn was following it and growing. And as Saturn was growing, it came to have a size that it had a gravitational impact on Jupiter, which became more important than the gravitational interaction between the gaseous disk and Jupiter. They reverse direction. And in a sense, you can think of Saturn and Jupiter feeding off one another and moving back out.
Gravity tugs each passing planet. This transfers orbital energy from one world to another.
All you have to do is exert a very subtle little periodic force at the right time, and you can have amazing changes in the motion of the object you're pushing on.
Once enough energy has been transferred, the planets synchronize their orbits. They are said to be in a resonance. For planets, resonances are achieved and maintained through the mutual push and pull of gravity through the fabric of space. They're a key factor in the continuing evolution of our solar system. This effect can be duplicated in the lab.
We have 10 metronomes here, set up on a swinging platform. They have little weights on pendulums here, but they've all been set at the same frequency. And I'm going to try to start them as best I can, completely out of phase, randomly. So their oscillation is going to transfer energy by the swinging of this plastic sheet to the other metronomes that are out of phase to get into phase with the majority. It's inevitable that there's going to be some majority group which starts out swinging more or less together, and they are eventually going to win out. Just doing this as randomly as I can. Aha, maybe in this corner I see 4 that are pretty closely synced. Yes, now it's more like 5, 6. Now you have one that's almost completely out of phase. So every time the majority hits a beat, it's going to give a little impulse, a little push to the platform, and that push is transferred to the metronome that's not in sync. Because the platform, you can actually see this platform vibrating back and forth in sync with the majority of these metronomes. Working on this one. So we're pretty close to resonance right now.
As the metronomes achieve resonance, it's important to notice how the platform shakes.
Now, it doesn't have to just be the force that's being transmitted by the plastic platform. It could be a force at a great distance, for example, the force of gravity. Just these small, little, seemingly insignificant pushes building up over multiple cycles can have dramatic energy transfer. That is how planets do it.
Like the metronomes, the two gas giants form a resonance.
We don't know exactly how long that took, but we have some fiducial marks for timing in the solar system formation, and that means that the grand tack had to have occurred relatively quickly, talking hundreds of thousands of years, perhaps, to a million years.
The two planets retreat until they reach their current positions. The sequence of planets as we find them today is based on Jupiter and Saturn's orbits. The planets eventually achieve a sequencing that many students learn through a mnemonic, such as, "My very educated mother just served us 9 pizzas."
Was there a time when the mnemonic was scrambled? Seems very likely the answer is yes, not to mention a lot of additional letters were probably in there as well.
Jupiter's menace of the inner solar system is finally over.
If Saturn had not formed at the right time in the sufficient size, Jupiter would have continued migrating in, throwing out out objects, unfortunate objects in the inner solar system, and ending up very close to the sun where it would stay. Yes, the Earth would be gone. Or the Earth would have had a terrifying encounter with Jupiter and would have had its orbit changed dramatically to gosh knows what.
There is mounting evidence that Earth had a terrifying visitor. Not Jupiter, but
Theia was this planetary body that was roughly the size of Mars. And through this collision, a lot of particles were ejected, probably completely destroyed. We don't really know how much of Theia was preserved.
Earth is rocked off its axis. Its surface liquefied. As a planetary body, Theia ceases to exist. Its remains are absorbed by the Earth and intermingled with the debris field. A new planetary body is formed, the Moon. Further evidence is found in rock samples from the Apollo moon landings.
This is a sample from the Moon, if you can see it. This was collected by the Apollo 15 mission.
Moon rocks contain isotopes identical to those found on Earth. When the Moon arose, it is first covered with a magma ocean.
People imagine the lunar magma ocean to be like this magmatic chamber I am describing, but at the surface and covering a whole planet. I see it as this ocean, like the Pacific, but this has to be like completely magmatic, orange, and like probably like fluxing around and probably moving.
Conditions in the lunar magma are as hellish as we can imagine. But a microscopic treasure forms in the magma: crystal zircons. These are the same gemstones used in jewelry. But the zircons in the Apollo moon rocks yield a different treasure.
So those zircon are very important because we know they crystallize in this lunar magma ocean. We know roughly when they crystallize in the lunar magma ocean. So they are one of these old pieces of the moon that we are looking for, one of these old pieces that we can use to date the origin of the moon.
Zircons not only give the age of the moon, they set a specific date for the collision.
The age of the moon is 4.51 billion years old.
4.51 billion years ago, Theia becomes part of Earth and forms the moon. But the story is not over. Space probes measure the moon slipping 3.8 centimeters further away each year. One day, the moon will break free. When that day comes, there will be no more tides, no more romantic moonlit nights. Could planetary orbits be inherently unstable? Could the chaos of planetary migration return? Haute-Provence Observatory, France. It's here that a discovery from a faraway star gives one of the biggest revelations about our own solar system. The story begins when Swiss astronomers Didier Queloz and Michel Mayor noticed something unusual about a star 50 light-years away in the constellation of Pegasus. Everything about this star is ordinary. A main-sequence mid-life yellow dwarf, just like our Sun. But with one strange difference. The star at Pegasus 51 is rocking back and forth. It's a weird anomaly astronomers have never seen before. They check their instruments. Everything is working, including their new spectrograph, a device that splits the starlight from Pegasus into rainbow colors. Hidden inside the colors are patterns of lines. By tracking the day-to-day movement of these lines, astronomers make a startling discovery. Pegasus 51 has a planet. But no one has ever seen a world like this. It's half the mass of Jupiter, yet it's extremely close to its star. 9 times closer than Mercury is to the Sun. The planet at 51 Pegasus must be inside the corona, broiling in temperatures over 1,000,000 degrees Fahrenheit. Soon, another planet is found around another star, and then another, and another. Astronomers have now confirmed over 3,700 exoplanets beyond our solar system. Nearly all of them are Jupiter-class planets grazing their host star. They're a new, previously unknown type called hot Jupiters. They're so numerous, hot Jupiters challenge theories about the origins of planetary systems.
It's very difficult to make a planet close to the star because there isn't enough mass to build a giant planet very close to the star, and there's gravitational frustrations for trying to build a planet very close to the star.
Astronomy is shaken with a new revelation. Planets do not stay put where they're born. When they're big enough, they migrate. It's a process called planetary migration. And yet, our own solar system has no hot Jupiter. Astronomers realize the Jupiter in our solar system was once on the move as well, but its migration was halted by a resonance with Saturn. Pegasus 51 shows where a planet lands when its migration is not blocked. The strongest evidence for the grand tack hypothesis comes not from our solar system, but from exoworlds charted around other stars.
Planetary migration is a universal concept. We see evidence of it out there in extrasolar planets, other solar systems. There's no reason why planet migration shouldn't have operated in our own solar system.
The New Horizons probe finds evidence for roving planets within our solar system. While charting ancient craters on Pluto and on the surfaces of its moons, the science team discovered many craters are the same age. This suggests that they were formed by a single event. Even way out here, tiny Pluto was smashed by a wandering planet. The Pluto catastrophe may be related to other planetary migrations in the outer solar system.
It was noticed that the exact orbits of the giant planets, particularly the outer giant planets, the icy planets, Uranus and Neptune, can be explained by their migration outward. There's a point in time about 3.8 billion years ago where Uranus and Neptune trade. And it's because of what some of these mean motion resonance interactions that we were talking about earlier. So this mean motion resonance involving Jupiter and Saturn and so forth just causes all heck to break out in the solar system. Uranus and Neptune, all of a sudden at 3.8 billion years, they literally swap places, and all that debris in the outer solar system gets flung inward towards the inner solar system.
The disruption in the outer solar system causes a new wave of violence. Astronomers call this epoch the Late Heavy Bombardment. Much of the cratering we see on our moon today is from this period. It may be possible that swapping orbits with Uranus is how Neptune got its moon. Today, the epoch of planetary migration appears to be over. The solar system seems stable, but what does the future hold? computer simulations reveal what may be the greatest threat to the solar system in over 4 billion years. It comes from a very special relationship between Jupiter and Mercury. Mercury's orbit is slowly perturbed, thanks to a subtle but constant gravitational nudge from Jupiter. A new resonance, like the one between Saturn and Jupiter that saved the inner solar system, is forming between Jupiter and Mercury. In 2001, computer models for the solar system were run 2,500 times.
They plug in the positions and the orbits of all the planets in the solar system in a computer, and they just let it run through time, through millions of years, hundreds of millions of years, billions of years, to find out whether or not these orbits are stable.
Change the location of one planet, say Mercury, by 1 millimeter, and you find that that change will give completely different predictions about where everything is going to be millions of years in the future.
To see how quickly and easily things can change, we have only to go back to our metronomes.
All I have to do is stop this platform from moving so that it cannot swing freely. Now, there's no way for the metronomes to influence each other. They're good metronomes, but they're not perfect. They can't be going at exactly the same frequency in the same phase, and they're just going to fall apart because they have no way of forcing the others to go to resonance.
The same applies to planets. Any small change can disrupt their harmony or restore it.
Now that the platform is free to swing again, it can again transfer energy and sync them up just like we saw the first time.
Scientists want to understand the consequences of a destabilized planet Mercury. In one case, Mercury leaves the solar system. The loss of its gravitational pull disrupts the balance of both Venus and the Earth. Earth and Venus swap orbits. The superheated atmosphere of Venus cools. Massive rains pour onto the face of the desert planet. Oceans arise. The land cools. And the air thins. Even the remains of an ancient visitor begin to cool off. Venus becomes like Earth. But the reverse happens to the Earth. As Earth settles into Venus's orbit, temperatures rise. The air becomes unbreathable. Glaciers melt. Oceans boil. The sun looms larger in the sky, only to be obscured by a thickening cloud cover. Suffering will be great, but brief. The entire 4 billion year pageant of life is cooked in a matter of days.
Complete and utter destruction and elimination of all life on Earth. I'm not just talking about higher life, I'm not just talking about civilization, but everything, a sterilization of the planet, is something that I would want to think about a bit.
Sterilized, uninhabitable, and quiet. There is another possibility, equally dark and apocalyptic. Crashes into the Earth, just as Theia did 4 billion years ago. The question is, could it happen today? Or is it a fate far away in the future? At a time when mankind itself is but a distant memory.
The problem is that
even with a perfect computer that understands all of the laws of motion perfectly, not just gravity, but all the other subtle forces that go into it, you cannot give it accurate enough initial information about the locations, the masses, the sizes, the speeds of all of the objects in the solar system.
Odds are, we may never see such a calamity. And yet, among the billions of stars in our galaxy, how many worlds are on the move? How many will share this fate?
By on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. It may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras, and its ancient creatures? And where did our world come from? How and when will it end? In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by our retinas, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Our days and our lives are short in cosmic terms. But with our minds, we have learned to follow time's trail out to longer and longer intervals. We know from precise measurements that the Earth goes around the Sun every 365.256366 days. Much of the solar energy that hits our planet is reflected back to space or absorbed by dust and clouds. The rest sets our planet in motion. You can see it in the annual melting and refreezing of ice at the poles, in the ebb and flow of heat in the tropical oceans, or seasonal cycles of chlorophyll production in plants on land and at sea. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time, as the Earth rotates on its axis, it makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. It can take a volcanic explosion or a dramatic lowering of sea levels to release this carbon back into the air, often after millions of years. The processes that shape a planet like ours play only the smallest of roles in the evolution of the universe. So to glimpse time's broader arcs, we must look to cycles that govern the larger cosmos. The reigning theory is that the universe began in a sudden expansion of space, the Big Bang. With entropy uniformly low, this was the time of the tiny. Subatomic particles like quarks and leptons stirred into a hot soup. They combined into atoms, setting in motion the primordial era. The universe cooled as it ballooned, growing dim and falling into what's known as the cosmic dark ages. After several 100 million years, larger clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. Trillions upon trillions of stars lit up galaxies all across the cosmos. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite to form generations of smaller stars like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the Sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the Sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. In time, solar winds push their outer layers so far out, they blossom in spectacular displays. That's just what happened about 12,000 years ago to the star that spawned the famed Helix Nebula. On the inside, spokes of denser gas stubbornly resist the star's relentless winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of Earth, but about 200,000 times more dense. This is likely what's in store for our Sun. A distant civilization may scan it for planets, but by then they won't see Earth. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars, and stars burning themselves out on a variety of timescales. In time, though, as the mass of the galaxy collects in successive generations of small stars, it will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way. At just about the time our Sun begins to swallow our planet, any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new, larger galaxy. Dust-ups like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. But a wholesale thinning out of the universe is inevitable in filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break. The distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues to how they got there. At more distant reaches of time, tens of billions of years from now, the sky will grow darker and darker as everything recedes away from everything else. A good place to be in those long twilight years of the stellar era is a place where gravity and energy have forged an extended truce. Perhaps a place like this. Not much larger than our planet Jupiter, a red dwarf is one of the smallest and dimmest stars in our universe. They have been shown to harbor planets close enough that their dim rays can sustain liquid water and life. Brown dwarfs and red dwarfs form the vast majority of stars in our galaxy. In fact, combined, their mass exceeds that of all the large stars. Because they burn so slowly, they'll be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as their host galaxies grow dim, another process will begin to transform these small outposts. Over time, chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling, and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era. Around a billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal: to define the final time horizons of our universe, as well as the final moments of its most persistent objects. Black holes, ranging from millions to tens of billions of times the mass of our Sun, occupy the centers of large galaxies today. As those galaxies age, over trillions of years of time, much of their mass will spiral toward the center, and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other. But when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. That has the effect of slowly siphoning energy and mass from the whole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider can pack. That is, unless there's more to nature and to gravity than we've thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the three spatial dimensions, plus time, that we experience in our everyday lives. We may be like an insect living on the two-dimensional surface of a pond, unaware of the deep and complex reality below it. It may be possible that an unseen extra dimension could intersect our world on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro-black hole could come from the extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. Its presence will open a brief window to a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when the clock strikes 10 to the 100th years from now, a number known as a googol. That's the end of the universe as we know it. But look beyond that to say 10 to the googol, a googolplex years. If you wrote all the zeros in that number in tiny one-point font, it would stretch beyond the observable universe. Will the great arrow of time have come to rest by then? Not if modern theories are correct. They hold that our universe is part of a much larger cosmic cycle of birth and death, with whole new universes coming into being in the space beyond our own. The time horizons of our universe may well be a blip in this grander scheme of things. Back to Earth now. We are products of the great era of stars and witnesses to its great spectacles of gravity and energy. No doubt there are other beings somewhere out there who are attempting to comprehend the universe. They too may invent the idea of time and develop their own theories on where it's all leading. Their discoveries and ours will not survive the entropy at work in the universe, as we all go the way of the stars, and as our universe gives way to grand new eras in the life of the cosmos. In a great cosmic pinball game we call our universe. How does energy stitch the cosmos together? And how how do we fit within it? We now climb the power scales of the universe. From atoms, nearly frozen to stillness, to Earth's largest explosions. From stars, colliding, exploding, to distant realms so strange and violent, they challenge our imaginations. Where will we find the most powerful objects in the universe? Today, energy is very much on our minds as we search for ways to power our civilization and serve the needs of our citizens. But what is energy? Where does it come from? And where do we stand within the great power streams that shape time and space? Energy comes from a Greek word for activity or working. In physics, it's simply the property or the state of anything in our universe that allows it to do work. Whether it's thermal, kinetic, electromagnetic, chemical, or gravitational. The 19th century German scientist Hermann von Helmholtz found that all forms of energy are equivalent, that one form can be transformed into any other. The laws of physics say that in a closed system, such as our universe, energy is conserved. It may be converted, concentrated, or dissipated, but it's never lost. James Prescott Joule built an apparatus that demonstrated this principle. It had a weight that descended into water and caused a paddle to rotate. He showed that the gravitational energy lost by the weight is equivalent to heat gained by the water from friction with the paddle. That led to one of several basic energy yardsticks, called a joule. It's the amount needed to lift an apple weighing 100 grams 1 meter against the pull of Earth's gravity. In case you were wondering, it takes about 100 joules to send a tweet. So tweeted a tech from Twitter. The metabolism of an average-sized person going about their day generates about 100 joules a second, or 100 watts, the equivalent of a 100-watt light bulb. In vigorous exercise, the power output of the body goes up by a factor of 10, 1 order of magnitude, to around 1,000 joules per second, or 1,000 watts. In a series of leaps by additional factors of 10, we can explore the full energy spectrum of the universe. So far, the coldest place observed in nature is the Boomerang Nebula. Here, a dying star ejected its outer layers into space at 600,000 kilometers per hour. As the expanding clouds of gas became more diffuse, they cooled so dramatically that their molecules fell to just 1 degree above absolute zero, the total absence of heat. That's around 1 billion trillionths of a joule. That makes the signal sent by the Galileo spacecraft as it flew around Jupiter seem positively hot. By the time it reached Earth, its radio signal was down to 10 billion billionths of a watt. Now jump all the way to 150 billionths of a watt. That's the amount of power entering the human eye from a pair of 50-watt car headlamps a kilometer away. Moving up a full 7 powers of 10, moonlight striking a human face adds up to 300 thousandths of a watt. That's roughly equivalent to a cricket's chirp. From there, it's a mere 5 powers of 10 to the low wattage world of everyday human technologies. Put 10 100-watt bulbs together. At 1,000 joules per second, 1,000 watts, that roughly equals the energy of sunlight striking a square meter of Earth's surface at noon on a clear day. Gather 200 bulbs. 20,000 watts is the energy output of an automobile. A diesel locomotive, 5 million watts. An advanced jet fighter, 75 million watts. An aircraft carrier, almost 200 million watts. The most powerful human technologies today function in the range of 1 billion to 10 billion watts, including large hydroelectric or nuclear power plants. At the upper end of human technologies was the awesome first stage of a Saturn V rocket. In 5 separate engines, it consumed 15 tons of fuel per second to generate 190 billion watts of power. How much power can humanity marshal? And how much do we need? Long before the launch of the space age, visionaries began to imagine what it would take to advance into the community of galactic civilizations. In the 1960s, the Soviet scientist Nikolai Kardashev speculated that a level 1 civilization would acquire the technology needed to harness all the power available on a planet like Earth. According to one calculation, we are 0.16% of the way there. This is based on British Petroleum's estimate of total world oil consumption, some 11 billion tons in 2007. Humans today generate about 2.5 trillion watts of electrical power. How does that stack up to the power generated by planet Earth? Deep inside our planet, the radioactive decay of elements such as uranium and thorium generates 44 trillion watts of power. As this heat rises to the surface, it drives the movement of Earth's crustal plates and powers volcanoes. Remarkably, that's just a fraction of the energy released by a large hurricane in the form of rain. At the storm's peak, it can rise to 600 trillion watts. A hurricane draws upon solar heat collected in tropical oceans in the summer. You have to jump another power of 10 to reach the estimated total heat flowing through Earth's atmosphere and oceans from the equator to the poles. And another 2 to get the power received by the Earth from the Sun. at 174 quadrillion watts. Believe it or not, there's one human technology that has exceeded this level. The AN-602 hydrogen bomb was detonated by the Soviet Union on October 30th, 1961. It unleashed some 1,400 times the combined power of the Nagasaki and Hiroshima bombs. With a blast yield of up to 57 million tons of TNT, it generated 5.3 trillion watts, if only for a tiny fraction of a second. That's 5.3 yottawatts, a term that will come in handy as we now begin to ascend the power scales of the universe. To Nikolai Kardashev, a level 2 civilization would achieve a constant energy output 80 times higher than the Russian superbomb. That's equivalent to the total luminosity of our Sun, a medium-sized star that emits 375 yottawatts. However, in the grand scheme of things, our Sun is but a cold spark in a hot universe. Look up into southern skies, and you'll see the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Deep within is the brightest star yet discovered. R136A1 is 10 million times brighter than the Sun. Now, if that star happened to go supernova, at its peak, it would blast out photons with a luminosity of around 500 billion yottawatts. To advance to a level 3 civilization, you have to marshal the power of an entire galaxy. The Milky Way, with about 200 billion stars, has an estimated total luminosity of 3 trillion yottawatts. A 3 followed by 36 zeros. The author Isaac Asimov imagined a galaxy-scale civilization in his Foundation series. Galaxia, he called it, is a superorganism that surpasses time and space to draw upon all the matter and energy in a galaxy. But who's to say that's the upper limit for civilizations? To boldly go beyond level 3, a civilization would need to marshal the power of a quasar. A quasar is about 1,000 times brighter than our galaxy. Here is where cosmic power production enters a whole new realm, based on the physics of extreme gravity. It was Isaac Newton who first defined gravity as the force that pulls the apple down and holds the Earth in orbit around the Sun. Albert Einstein redefined it in his famous general theory of relativity. Gravity isn't simply the attraction of objects like stars and planets, he said, but a distortion of space and time, what he called space-time. How a totally dark object can do this has been narrowed by decades of observations and theory. If a black hole spins, it can turn into a violent cosmic tornado. Gas and stars begin to flow in along a rapidly rotating disk. The spinning motion of this so-called accretion disk generates magnetic fields that twist up and around. These fields can channel some of the inflowing matter out into a pair of high-energy beams, or jets. Gas and dust nearby catch the brunt of this energy, growing hot and bright enough to be seen billions of light years away. Amazingly, the power of a black hole can rise to even greater extremes at the moment of its birth. As a giant star ages, heavy elements like iron gradually build up in its core. As its gravity grows more intense, the star begins to shrink until it reaches a critical threshold. Its core literally collapses in on itself. That causes the star to explode in a supernova. And now, in death, the star can unleash gravity's true fury. In the violence of the star's death, gravity can cause its massive core to collapse to a point, forming a black hole. In some rare cases, the newborn monster powers a jet that accelerates to within a tiny fraction of the speed of light. For a few minutes, these so-called gamma ray bursts are known to be the brightest events since the Big Bang. 3 orders of magnitude above a quasar, at a billion yottawatts, a 10 with 42 zeros. Remarkably, they are still not the most powerful events known. Albert Einstein's equations contained an astonishing prediction: that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. They produce a series of waves that move outward, like ripples on a pond. Scientists are now hoping to detect these gravitational waves and verify Einstein's prediction using precision lasers and some of the most perfect large-scale vacuums ever created. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they are hoping to record the collision of ultra-dense remnants of dead stars known as neutron stars and of black holes. According to computer simulations, as 2 black holes spiral into a fateful embrace, the energy carried by each gravity wave rises 5 orders of magnitude above a gamma ray burst, to 100 billion trillion times the power of our Sun. Does the collision of black holes define the known power limits of our universe? Perhaps not. As turbulent as the environment of a black hole might be, its true power may well lie deep in its core. A black hole's mass is enshrouded within a dark sphere called the event horizon. Since the 1920s, scientists have described the mathematics of the event horizon as the equivalent of a waterfall. It's the point of no return, beyond which water falls freely into the gorge. At the event horizon of a black hole, space itself falls freely in at the speed of light. If the black hole is spinning, then the flow spirals down and around an inner horizon that envelops the singularity. That's the central region where space-time becomes infinitely warped. Any matter that rides this river of space whips around the inner horizon so fast that centrifugal force tends to fling it back out. As that happens, it collides with matter that's streaming in, whipping up a ferocious cosmic storm. The energy of the colliding stream feeds upon itself, rising to what may well be a limit imposed by nature. It dissipates only as it falls into the singularity and disappears. Fortunately for us, gravity walls off such energy extremes behind the event horizon, where they cannot affect the rest of the universe. And so here we sit. Our world is nestled within a vast stream of cosmic energy, somewhere between the spin of an electron and the maelstrom of a black hole. There's no telling whether a future Earth civilization will be able to harness enough energy to advance into the cosmos. For now, as we tap into the tiny morsels of power at our disposal, we venture a closer look at a universe blazing with activity. We are its product, and its starstruck admirer.
To shreds in a flash, collapse in on itself? Or will it slowly freeze to death? Scientists are imagining the unimaginable, and they're coming up with some wild ideas about how it's all going to end. This is the end of the universe. A battle is taking place in the farthest reaches of space. No one can see it, but scientists are certain that it's happening, and that the outcome is grim. The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. the universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy. It's moving outward. But eventually, there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now, what I did the focus on was a V equals 12.
There it is, yeah. Okay, that's the bright star. We have
Get a better focus now. That was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine. We're looking back in time to study distant galaxies, seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat, but when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, he's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift is the cornerstone of the quest to pin down the fate of the universe. Clearer pictures of the universe that have only been possible in recent years have led cosmologists to conclude that the redshift of distant galaxies is greater than predicted. This is startling. Not only is the universe expanding, it's speeding up. Nothing in the observable cosmos could account for an accelerating universe, and yet the data seem irrefutable. This has to mean that an invisible force is working against gravity. Cosmologists have come up with a name: dark energy.
So when the universe was young, gravity was the most dominant force. And so what we see here is galaxies as particles on the surface of the water are bound together by gravity. And at a point about 7 billion years ago, dark energy and gravity are pretty well in balance. But the universe continues to expand, the density goes down, and so dark energy starts to take over. And lo and behold, the universe starts to accelerate. So dark energy is now the dominant property of space.
So the universe started out with a certain amount of energy, and we know we're trying to understand how much energy there is, and we know the universe is expanding as it moves outward with time. We also know now that the universe's expansion is accelerating, and we don't know, is that acceleration going to slow down or not? We're still trying to understand that. So in understanding what's going to happen to the fate of the universe, we have to know how much energy is there, how much matter is there.
The history of the universe is really a battle between dark matter and dark energy. These two forces are in opposition, and so both the history of the universe and its ultimate fate is really the competition between these two forces.
The Big Crunch theory was a result of scientists interpreting that dark matter is the dominant force, but astronomers now suspect that dark energy might be much stronger. If so, the end could be dramatic and violent.
It pulls apart solar systems, it pulls apart stars, and eventually it grows so strong that it pulls apart matter itself, breaks bonds, pulls apart atoms, and reduces everything to fundamental particles, and that's the end of the universe.
The battle between dark matter, the force that holds the universe together, and dark energy, the force seeking to tear it apart, has set the universe on a path of destruction. If dark matter is the victor, the universe might collapse. If dark energy rules the cosmos, it could rip to shreds.
The expansion grows so strong that it tears up the entire universe.
It'll be a strange twist of fate. Dark energy, the force that propelled matter to form a magnificent universe, continues to push it outward and drives it to its demise. To find out if dark energy is in fact winning the battle, scientists will first need to know how fast the universe is actually expanding.
The most remarkable feature of the universe is that it's expanding. Every galaxy is moving away from every other galaxy. When you look out into the night sky, you see distant stars, galaxies, clusters of galaxies they observe with telescopes, and they're all moving away from us. We can illustrate that with this balloon. As we expand it, we see that every dot drawn on this black balloon, like the night sky, is moving away from every other dot. But there's something else that we know about the universe, something else that we know about the expansion. That is that the expansion is getting faster. The universe is accelerating. The size of the universe is getting bigger at a faster and faster rate. And we don't know exactly how fast it's accelerating, but if it's accelerating fast enough, then something really dramatic could happen. The universe could end up tearing itself apart in a big rip.
This is perfect. This is great that you rigged this up. So this is a giant version of the demo that I do in class.
Dr. Robert Caldwell attempts an earthbound experiment to show how dark energy affects the acceleration of the universe. He uses a paintball gun mounted on a truck.
Yeah, and basically, I mean, we could adjust the angle in any way that you want it. What do you think about this?
I think down at the
Down
ground,
a little bit more.
is the best, so we can mark each
How's
time
that?
the gun fires. That'll be good.
All right, let's try that.
He sends the truck coasting down an incline. Earth's gravity pulls the vehicle downhill, which is similar to how dark energy propels the universe outward, causing it to expand. Gravity pulls the truck forward at an increasing speed. The gun fires paint at the ground at regular 1-second intervals. Caldwell measures the distance between the paint dots to calculate just how fast the truck was accelerating. He'll use the data from this experiment to see how gravity's force compares to dark energy's force in the cosmos.
We started thinking about the Big Rip when it was discovered that the expansion of the universe was accelerating. The degree of acceleration is not known, and it's the subject of a lot of effort by astronomers today to try and figure out exactly how fast the expansion is growing. What is the past evolution of the universe in detail, and if we can glean from that, what is the future evolution of the universe? It's not known exactly how fast it's accelerating. There's some evidence that the acceleration is beyond a certain threshold, and beyond that threshold, there's a runaway effect that could take place, and it would rip apart the universe.
Good luck. Fantastic. I think we've got some good data.
Excellent. How do we measure this?
Great. Give you that end.
All right.
I'll take this.
5 feet, 8.5 inches.
The point of the paintball experiment is to find parallels between the truck propelled by the invisible force of gravity and the accelerating universe.
I'm glad we got the long tape measure because it's really growing pretty fast, the interval.
Within a few measurements, the distance between the paint spots increases by nearly 7 times. If the truck were in space, at this rate, it would travel faster than 100 miles per hour within a minute, and over 1,000 miles per hour within 10 minutes.
They're getting big now.
Here we got 42.5 feet.
42, all right, 0.5.
The question for Robert Caldwell is whether the same kind of expansion and acceleration are happening on a cosmic scale.
What's the capsule made of? Is it plastic or something?
Gelatin.
Uh-huh,
It's
okay.
all biodegradable.
Uh-huh.
So you could actually eat them if you wanted to.
This right here is the data that I took with Eric, the cumulative distance traveled by the car as a function of time, and that's beautiful. It's this nice parabolic shape. That's exactly what you expect for an accelerating body. Now over here I've got another calculation going on where I'm working out the acceleration of the universe.
Robert Caldwell's calculation shows that forces on Earth are similar to forces in space. This demonstration, then, gives a sense of the dramatic rate of expansion that appears to be happening in the cosmos.
By eye, it might be difficult to appreciate how good a fit it is, but I can tell you that the weight of the statistics indicates that an accelerating universe is a very good fit to this data.
If, like the truck, the universe is continually accelerating, then billions of years from now, the universe might tear itself apart.
All the distant stars and galaxies will be pulled away from each other. They'll be pulled away from us. But moreover, we won't have time to grow cold and lonely. It'll actually be pretty exciting and dramatic and violent. Stars are ripped apart, planets are ripped apart, and even atoms are torn apart before the universe ends. It wouldn't happen for at least 50 billion years, but still it's an interesting fate for the universe.
What would atoms ripping apart look like? Things like coffee cups are solid. Atoms join together to create something that will hold a cappuccino without leaking a single drop. Zoom in through the cup, like sailing through the cosmos, past the molecules and into the atoms. The solid cup is nothing more than a fabric of atomic particles that formed a bond to become matter. If these particles were to move apart, the bonds that hold this cup together stop working. The atoms no longer support molecules. The connections between the minuscule particles dissolve. Matter in the form of this cup ceases to exist. It disintegrates, gone from existence. This is the dramatic end that Robert Caldwell foresees for the universe.
What you would see if you were standing on Earth or standing on some other planet that happened to still be around at that time, you would see something that looks like a wall of darkness approaching you. And as the wall of darkness approaches, stars would go out, galaxies would go out, and then eventually that wall of darkness would surround the planet. And then pretty soon, atoms themselves are torn apart, and that's it. Just the wall of darkness shrinks down to a point, and that's the end of the universe.
According to Robert Caldwell, that moment is still billions of years off, leaving plenty of time to refine the research.
In a way, this is like a detective story. We're trying to figure out what is the culprit, or who is the culprit responsible for the cosmic acceleration. We think we know its name. We call it dark energy, but we don't know the modus operandi. We don't know exactly how it works. And what's needed is more information about the physics behind the dark energy. We want to know exactly what it does and exactly what it's made out of. And in answering those questions, we'll be able to figure out exactly what is the fate of the universe.
The Big Rip is one theory. Cruising just above Earth's atmosphere and peering deep into space, the Hubble telescope provides scientists with clues to a less violent, but equally unavoidable, end of the universe. Scientists now say the universe is expanding, and that depending on how fast it is accelerating, it might end in a big rip where everything tears apart. It's also possible that it will continue to expand, but at a slower rate. The universe wouldn't rip apart, but would become dark, cold, and lifeless.
If dark energy turns out to be constant, a constant property of space, and continues at the same rate that it is now, the universe will keep expanding forever, and it will be a very sad state. I think in the end, it just chills out. Everything cools down.
Evidence for the Big Chill and all of the theories for the end of the universe, in part, come from the Hubble Space Telescope. It has been orbiting Earth since 1990 and has an unobstructed view of the cosmos. The extraordinary images it beams back to Earth are amazing in their clarity and detail. And because of Hubble, scientists can make better predictions about how the universe will end.
So here is an example of a very deep field that was taken by the Hubble Space Telescope. Literally, you point the space telescope at a single region in space. And if you looked at this from a typical ground-based image before Hubble was launched, first of all, it's literally almost size of a postage stamp. And so suddenly, the first Hubble deep field that was ever taken had 4,000 galaxies that looked just like the galaxies here, that were never visible before from the ground. A tremendous power. Each of these smudges in their own right is another galaxy. Each one of these galaxies contains about 100 billion stars.
Hubble sees more than just stars and galaxies. It just might be onto one of the key ingredients of space, an invisible ingredient that could put the brakes on dark energy's effect and cause a big chill. That's dark matter. Scientists talk about dark matter as the substance that holds the universe together and could prevent a big rip. Evidence that dark matter exists is seen in some of Hubble's images of nearby galaxies. It sometimes appears as though other galaxies surround them. The other galaxies are not really there at all. Rather, they are reflections of more distant galaxies coming from behind. Astronomers suspect this optical illusion is dark matter causing a weird distortion of light called gravitational lensing. The light from the more distant galaxies is literally bent by the curvature of space caused by stars and dark matter in its path. The more dark matter there is between Earth and the distant galaxy, the more the light will be bent and the greater the force to cause a big chill.
The gravitational lensing is a tremendous tool for the astronomer because we can measure the distortion in background galaxies and use it to trace the distribution of dark matter on various scales. We're looking at a distribution of idealized galaxies here on the sky, and the light from these distant galaxies is passing through pumps of dark matter. What you look at is not really what's happening. It's a bit like wearing spectacles and not knowing that you're wearing them.
And if you can tell how much that bending is occurring, you can map the dark matter, and you can also see, well, if there's dark matter there, is the universe around that dark matter behaving the way it should given the gravity or not? If it's slightly gravitating less, then dark energy might be changing in those places.
Identifying which energy force dominates, dark matter or dark energy, will give scientists more confidence about whether a big chill or a big rip will be our fate. The best evidence shows dark energy as the driving force, but by how much? Solving this mystery depends on astronomers finding ways to measure how fast the universe is moving. On Earth, it's simple to determine how fast something moves. An airplane, for example, is relatively close. We can look at it and calculate its speed by estimating the distance it travels and timing how long it takes to get from one point to another. But a star's light can travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces in stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the big chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a big chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward. Dark matter slows them down. In a big chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter, and much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place, but in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
Assemble all those difference measurements and make a map of what the variations are like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?
To get from one end of the solar system to the other by driving. Because space is so huge, we're bringing it down to Earth by scaling the distances in our solar system down to the size of the continental United States and placing the planets along our route. It's a 3.6 billion mile road trip, shrunk down to under 3,000 miles. My name's Colonel Chris Hadfield. When I was 9 years old, I saw the impossible happen. And from that moment forward, I wanted to make the impossible happen for me and to turn myself into an astronaut.
We have booster ignition and liftoff of the Space Shuttle Endeavour.
I've been a mission specialist on a space shuttle, the commander of the International Space Station. All told, I've logged almost 4,000 hours in space. I've flown through it, I've walked in it, I've even sung in it. But now, I'm driving it. Our road trip across the solar system starts here on Long Island, New York. That's the sun off the northeast coast. It's 10,000 degrees Fahrenheit on the surface. That's like 40 times hotter than my NASA spacesuit was designed for. But I'm going somewhere a little bit cooler. On this journey, I'll be joined by some amazing people, riding shotgun and guiding my adventures. So it's time to pick up my first passenger. Come on in. How are you? How are you? It's world-renowned astrophysicist Michio Kaku of the City University of New York.
That's right. I've heard so much about you.
I've heard lots about you
You
as
serenade
well.
the masses from outer space, right?
And I've been watching all the stuff you've been doing from afar. I think it's nice to have a little look at the world and the universe together.
Grand tour of the solar system.
The first leg of my journey will take us through the inner solar system to Mars. Mars has always held a grip on my imagination. And we're getting tantalizingly close to the day when an astronaut will actually step down onto the red planet. But there are many other wonders along the road from the sun. Look, there it is. Mercury, the first planet from the sun. Mercury is an average of 36 million miles from the sun. But here in the miniverse, it's just 24 miles down the road. It looks a little like the moon, which is a place I've always wanted to go.
Many people think that, well, being on Mercury is very similar to being on the moon. No. If you were an astronaut, the sun is this huge fireball lighting up the sky, dominating everything you see around you. It would be quite a hostile environment with the sun just literally staring you in the face.
Yeah.
And it's blisteringly hot on the surface. It's 800 degrees Fahrenheit.
Wow.
Imagine you being able to bake a pizza in your back porch without an oven. But Mercury also has some surprises. You realize that there's ice on Mercury?
Like water ice?
Water ice, right. It turns out if you go to the poles, the North Pole and the South Pole, and look at the bottom of craters where you have permanent shadows, we think there's evidence of water ice.
So even that close to the sun, there are places that are permanently in the dark.
That's right. This shocked a lot of scientists who have this image of Mercury being this hellhole.
Beyond Mercury, we chart a course for Venus. In the universe, it's about 31 million miles. Which means, in the miniverse, Venus is only about 20 miles away. Venus and the Earth are almost the same size. For a long time, astronomers thought Venus was a kind of twin sister to our planet. But apparently, it's Earth's evil twin.
You know, when I was a kid, I read science fiction novels that said that astronauts of the future will vacation on Venus. They'll have tropical environments and swim in the oceans of Venus. Boy, were they wrong.
Tropical environments, I think that was a bit of an understatement.
Temperatures approach 900 degrees on the surface of Venus.
Hotter than Mercury.
Yeah, and it rains sulfuric acid, and the atmosphere is so thick. The pressure is so great on the surface of Venus, it's like being half a mile underneath the water in the ocean.
So that's like being way, way underwater with the pressure of the water all around you.
Yeah, even submarines. Submarines will be crushed like an eggshell at that depth. You know, here on the planet Earth, we experience pressure on our skin 15 pounds per square inch of your skin. On Venus, it's 1,500 pounds of pressure per square inch.
So it's sort of like in a spaceship when the engine's light and you're crushed back in your chair, except it's crushing you from all directions, not just from one side.
Right. So if you're an astronaut walking on Venus, you'd be crushed like an eggshell. I make a great tour guide, huh?
Maybe not such a good salesman, though. I'm not sure. You should not be selling real estate on Venus.
I'm selling Mars, actually.
Okay. Ah, here we are.
Who would have thought that this jewel hanging there in the sky is bright because of sulfuric acid droplets?
And yet we've built spaceships that have made it all the way to the surface, right?
Just for a few minutes, and then they got fried.
So it's the hottest planet in the solar system, and sulfuric acid is raining from the sky.
That's right. So if I was a tour guide, I'd say, maybe we should skip Venus this year.
As we leave Venus, we're headed for the only planet I've actually orbited as an astronaut. And the inner planets are so close to each other that to get there, we still won't be leaving Long Island.
I think you're going to recognize our next destination.
It's terra firma. It's our home world.
Home sweet home.
Yeah. We take it for granted, right?
Yeah.
But most of the universe is quite hostile. All these planets that are blisteringly hot or freezing cold,
Yeah.
It's great to find one that's just right to have life on it.
And there's my old home away from home, the International Space Station. I spent 5 months there, taking in the view every single moment I could.
And look, you can also see the northern lights, the southern lights.
Beautiful. I've had the great privilege of seeing the aurora in a way only a handful of people have.
I was outside on a spacewalk. It was on the dark side of the Earth.
Of course, I was just by happenstance just outside doing a spacewalk.
I had my lights shut off, my eyes had adjusted to the darkness, and we went into the southern lights, the aurora australis. They were rippling between my legs and pouring by. They're mostly like green and red, as you've seen in the pictures, but in them you get all the little subtle colors as well. I couldn't convince myself that even though I knew it was real, it was just hard to somehow accept the fact that this amount of gorgeous, pulsating light and color could be a natural, real thing. It was one of the most magnificent experiences of my life. Plus, we're going 5 miles a second, so it's almost like if you watch the surf crashing on the shore, but then you're skimming through it on a board, so you get your own added speed, like a surfer on a wave. Makes it even more magnificent. It's just...
Well, see, that's the title of your next book, Surfing on the Aurora.
Maybe you're a better travel agent than I thought. Surf the Aurora. I like it.
Well, I've left Earth before, and I'm doing it again. And this is a journey I've dreamed about many times. From Earth to Mars. A world that has the best chance of becoming humanity's next home. Even when Mars is closest to us in its orbit, traveling there in a spaceship will take between 6 and 9 months. In the Miniverse, it's just down the Brooklyn-Queens Expressway. Sounds like a quick trip, but in the Miniverse, we have to deal with rush hour.
So how soon do you think until it's not just robots going there, but people?
Well, you know, going to the moon was a piece of cake. 3 days.
There are
you're
people
on the
that would
moon.
disagree with you.
Everything's relative.
Yeah.
To go to Mars, let's face it, it takes months.
Yeah.
NASA's laid out a tentative timetable. We're talking about the 2030s, just to orbit around the red planet, and perhaps by 2040 actually landing on there.
Wow.
Unless, of course, private enterprise catches up, in which case we'll be on Mars even sooner.
Yeah.
Would you want to go to Mars?
Oh, absolutely. Yeah, in a heartbeat. I'd love to. The idea of that early exploration and discovery, that's what always has made my heart beat faster. Yeah, if it were easy, I don't think I'd really want to go, but the challenge that makes it possible, to me, that is what really makes me want to go.
But for me, nah, I don't think so. First of all, being a physicist, I know the odds of success. 1% of the spacecraft will blow up and never reach Mars.
Sounds like physicists are pessimists to me.
No, realists, that's all. It's just realists.
But that means 99% of them make it, you know? I think Mars is worth the drive. So if I sign up to go to Mars, if I stick my hand up way high and get picked, what do you see as the biggest hazards between here and there? Is it getting hit by small meteorites? Is it the radiation?
I think it's all of the above. Yeah. Especially radiation. Radiation from the sun, cosmic rays. Radiation causes premature aging. At best, your body will age faster than normal, and at worst, cancer.
You know, something else, having spent half a year in space, one of the beauties of being on the International Space Station is you got the world in your window all the time. But as soon as we turn tail to Earth, fire the engines, and start going to Mars, within a week or two, Earth is just a little dot, and you have nothing out the window for 6 months, 9 months, however long it takes. I think you can't play down the psychological effect of that.
Right. So my attitude is, let someone else get all the ticker tape parades.
Despite all the challenges, Mars pulls at my imagination. It's a place where humanity has long hoped to find the first signs of alien life.
For the most part, we see no evidence of life whatsoever. You know, some people think they see a face on Mars, and there's one formation that looks like Kermit the Frog, actually, on Mars.
I haven't seen the Kermit the Frog formation.
But they're optical illusions.
There's evidence of methane in the atmosphere, which can come from microorganisms, but doesn't have to. Traces of water might bubble up to the surface, but might be too salty to support life. But there's also water in the ice at the poles.
Journalists say follow the money. Physicists and astronomers say follow the water.
Follow the water.
Where there's water, there could be hydrocarbons, organic chemicals, and who knows, maybe even an alien form of DNA. Wow, you can really see Mars in its full glory. I mean, you can see why the ancients named it after Mars, the god of war, because it's so red.
Red like blood.
Or like rust.
Or like the bridge, right?
That's
Rusty,
right.
like the bridge.
Sometimes that rust in the soil gets kicked up by the Martian wind. So if I was standing on the surface, the sky would be pink, not blue.
You know what amazes me is to think that right now on Earth there are a few people in darkened rooms operating controls that are driving robots around on that planet right now. And that maybe not too long from now, people will have a chance to go all the way there actually in person.
There'd be many wonders to behold on the surface of Mars, but the one I want to see most is Olympus Mons. It's the biggest mountain on any planet in the solar system.
It would extend from here, New York City, all the way into Canada.
And how high?
It would be like, well, take 53 of those Freedom Towers going all the way up.
53 of those? Wow.
Yeah, imagine 53 of them stacked vertically on top of each other.
Wow, that's going to go out of sight, wouldn't it?
That's 16 miles high, 3 times taller than Mount Everest.
And you don't want to be the astronaut that plants the flag on the top of Olympus Mons there?
No, I'll let someone else have the glory. But that's the lure of Mars.
As I drive Michio back to his home in the city, I wonder what home would look like on Mars.
So instead of building a dome like in science fiction novels, why not use the volcano tubes that already exist? Tubes that once had liquid lava flowing through them can also be used as caves for the astronauts, protected from the cosmic rays, the solar flares, and the micrometeorites. That'd be the quick and dirty way to get a Mars base off the ground.
It was an absolute delight, Professor, to travel the inner solar system with you.
Right? It's been a cosmic tour to the universe.
Thanks. I look forward to seeing you somewhere else around the solar system.
We covered 141 million miles in the solar system without ever leaving New York. But that's about to change. Like a pioneer pushing into a vast, uncharted wilderness, I'm ready to leave the familiar surroundings of the inner solar system for the strange and mysterious realm of the outer planets.
In other words, I'm headed to Philadelphia.
In the inner solar system, we passed 4 planets in less than 100 miles. Things are going to get a lot more spaced out. In the universe, the average distance between the Sun and Mars is 141 million miles. Then, the average distance from Mars to Jupiter is 342 million miles. In the miniverse, that's like a trip from New York to Washington, D.C.
Whoa! Halfway between Mars and Jupiter, there's an enormous ring of rocks called the asteroid belt. That one just missed. Yikes. The asteroid belt has millions of small particles.
It also has about 750,000 bigger asteroids, some of them more than 3,000 feet across. Some people think that the asteroid belt looks like the world's most dangerous video game.
But in real life, there's an average of about 600,000 miles between each of the significant asteroids.
Even in the miniverse, that's about 1/4 of a mile. Still, plenty of space to maneuver through safely. So I've made it to Philadelphia in one piece. As I head for the outer planets, I'll need a guide who really knows this part of the solar system.
Hey, come on aboard.
Why, thank you.
It is the chief astronomer and planetarium director of the Franklin Institute in Philadelphia, Mr. Derek Pitts.
You got
Welcome
it.
to my spaceship.
How are you, Chris? Thanks a lot.
Ready. Are you ready to head across the solar system with me?
I'm ready to take a trip through the planets.
All right. So we got some big planets coming. Glad to have you aboard.
I'm looking forward to it. This is the first time I've actually taken a trip through the outer solar system.
Well, this is the first time for everything. So the beauty of shrinking the whole solar system down to the size of the U.S. is you get through the asteroid belt fairly quickly.
We're on the road to Washington, D.C. Drawn in by the immense gravitational pull of the most massive planet in the solar system. Jupiter's almost 88,000 miles in diameter. That's 1,300 times bigger than Earth. You could actually fit Earth and all the other planets inside Jupiter and still have room.
And in fact, Jupiter itself weighs more than all the other planets of the solar system put together twice.
Wow. It's the heavyweight.
It is big.
Jupiter's huge, but even with all that mass, there's no place for an astronaut to put a footprint.
It's really just a big, big ball of gas.
Wow.
Hydrogen, helium, methane, ammonia.
Wow.
But as an astronaut, What would it look like to take my spacecraft and start diving down into Jupiter?
You'd have a very interesting trip as you descended down into the clouds of Jupiter. First of all, you'd start down into the cloud tops of maybe several thousand miles. You'd start to notice that you're losing sunlight and things are getting darker. But you'd begin to pick up lightning. You'd see flashes all around you.
If you get right to the very center of Jupiter, what's right there in the middle?
Well, oh my gosh, the pressure increases so much that gaseous hydrogen can be squished down until it becomes a liquid, and then it turns into something very interesting called liquid metallic hydrogen.
Liquid metallic hydrogen. That sounds like a science fiction movie.
I wish I could explain it, but I don't think I
You know
can
that
even
creature
tell you what
that
it's like.
drags himself up out of that
Out of
silver
the
liquid?
ooze and
That sounds like liquid metallic
I think
hydrogen.
that's where
to
that
me.
guy came from.
Yeah,
Yeah, well, in any case, right down in the middle of all this liquid metallic hydrogen, there might be a rocky core, a solid core inside that.
So if you get right to the core of Jupiter, I mean, what sort of pressure are you actually facing there?
All right, so the pressure at the core of Jupiter is about 30 million times the surface pressure here on the Earth.
So
if you start at about 6 feet tall, by the time you get to the center of Jupiter, you're going to be about a half an inch tall. But you also have extremely high temperature down there as well, about 63,000 degrees Fahrenheit. About 6 times hotter than the surface of the sun. So if you're an astronaut going into this, you're going to have a beautiful light show for the first half of your trip. And then the next half of your trip is going to be like the worst horror show nightmare you've ever experienced.
Wow. Yeah, I'm going to have to really rethink my my Jupiter spacesuit.
I think you might want to go with the space probe thing instead.
Yeah.
Okay, so maybe it's safer to let spacecraft like the Juno probe go inside Jupiter.
Great. Approaching Jupiter.
But to orbit Jupiter, to see it up close, would be one of the most amazing experiences in the solar system.
Whoa. Look at that, right above the... Holy cow.
You know, I knew it was big, Chris, but this is really incredible.
Look at the colors of that. That's amazing.
And look at the detail you can see in the cloud tops.
Wow.
All the little whirlpools.
That's worth the trip.
It is definitely worth the trip.
It makes sense that Jupiter's over Washington, D.C. Washington's influence is felt all over the world, just like Jupiter's influence has been felt all across the solar system. Its gravitational pull is so strong, it acts like a cosmic vacuum cleaner, sucking in comets and asteroids that might otherwise rocket into the inner solar system and strike our planet. As an explorer, I'm often drawn to the things that frighten me the most. On Jupiter, it's the intense violence of the monstrous Great Red Spot.
Whoa. That's incredible. And the red spot right over here coming across this way.
It's a ferocious storm that may have been churning for 300 years.
It's really spectacular.
If I could orbit Jupiter at the same altitude that the space station orbits our planet, the Great Red Spot would fill my entire field of view. It's just that big, larger than the whole Earth.
That's a view and a half.
That really is amazing.
I flew through a lot of bad weather when I was a fighter pilot. I wonder what it would be like to drive through the Great Red Spot.
Are you serious?
Yeah.
That's an awfully dangerous thing to do.
The center is relatively calm, but as you near the outer edge, the winds climb to 400 miles per hour, twice as fast as the worst hurricane winds on Earth.
Okay. When you're flying through the Great Red Spot of Jupiter, remember, keep your windows up and your air conditioning on.
And that's because the red spot is full of ammonia and ammonium sulfite. Not good stuff.
Not good.
As we speed away from Jupiter, I'm reminded of the Cassini spacecraft that visited here in the year 2000. It sent back some unforgettable images before using Jupiter's gravity to slingshot towards its ultimate destination, Saturn. I've been lucky to see many spectacular sights in my time as an astronaut, but I've always thought that nothing would be more stunning than to see the rings of Saturn up close with my own eyes. It took the Cassini probe more than 3 years to make the trip from Jupiter to Saturn. But in the miniverse, Saturn's just 6 hours away in West Virginia.
Got a bit of road to cover between now and then.
And it looks like we won't get to Saturn till after dark. Good thing we space explorers always pack snacks.
Well, look.
Look at that.
We got some astronaut ice cream.
Oh, my favorite.
How's that? Let's try some of this.
Can I have a piece?
Sure. Let me give you a hunk
It's
there. There we go.
The attractive color you'd hope your space food would be.
Cheers.
Cheers.
It's not as bad as I thought it was going to be.
So I do have to fess up, though, we do not have astronaut ice cream on the space station. It tastes nice, but it's just too crumbly and not practical for weightlessness.
Right.
There's going to be stuff in your nose, in your eyes, in the computers.
This would be a mess everywhere.
Not bad for the miniverse, though.
No, it's good for the miniverse.
So let's just talk about the planet itself. You're an astronomer. What can I expect when I get to Saturn?
It's the rings.
It's got rings.
Everybody
right.
loves the rings.
Yeah.
All the gas giants have rings, but none of them can match Saturn's.
You're measuring about 176,000 miles across.
That's wide enough to line up 22 Earths side by side.
If you were flying your spaceship right next to the rings, what do you think it'd look like up close?
If you're right up close on it, it really would look like a very well organized rubble field, because you have these particles of different sizes. You know, you're down to something that is dust size, and maybe up to objects that are the size of a small car or even a small house. But they're all in there together.
From just a little distance, the rings don't look like a rubble field at all.
Wow.
Look right there.
That is spectacular.
Wow, you can see everything. You can see the colors and the delicate swirls and the rings.
The rings really are spectacular. Oh my gosh.
Saturn has dozens of moons, and at least 3 of them have underground oceans. Those are Dione, Enceladus, and Saturn's biggest moon, Titan. For a moon, Titan is pretty titanic. Even bigger than the planet Mercury.
Titan's really a wonderful place to visit too, because it's the one place in the solar system that we know of that has oceans on the surface.
Titan has oceans of what?
Ah, there's the catch. A lot of it is methane that's actually out on the surface, pooling in lakes. It also has a cloud cover that actually rains methane down onto the surface.
Wow, so methane rain.
At about 300 degrees below zero.
Oh, wow. So, you know, the suit that I wore for my spacewalks, I'm not sure that it could put up with the huge temperature extremes that we're seeing on the moons of Saturn.
You need something really special.
I don't think thick socks are going to help.
You need a little bit more than that.
You know, sleeping on a space station, you dream about views like this. When you close your eyes, sleeping on a spaceship, sometimes you see flashes of light with your eyes closed. It's the radiation and the high-energy particles from the universe that are going through your optic nerve and making your vision flash. It's a real reminder of that you are somewhere other than Earth.
You don't see this on Earth, do you?
No, because our atmosphere soaks up the little particles that cause this to happen in our eyes. And I can imagine the first astronaut, the very first one who saw that, is probably going, I don't think I want to tell anybody. I'm seeing flashes when I close. I could see two astronauts going, "Hey, do you see flashes?"
See anything like that? So
Going, yeah, oh, we all do. Oh, okay.
That's a really special experience.
It's part of what astronauts dream about.
I hate to leave, but I have more planets to visit. And Derek's got to get back to Philadelphia. Time to part ways.
Chris, it's been great.
It has been wonderful touring the solar system with you.
Thank you so much for taking me around. I've had a great time seeing all these planets so close.
I got a little bit more of the solar system to see, but thanks for being a tour guide
Well,
for
look,
me.
you have a really great trip.
Safe travels home, sir.
All right, Chris, take care now.
All right, bye.
As for me, I need an early start. Because after Saturn, distances between planets get extreme. So there's no time to waste.
This is what's amazing. Our trip from here to the next planet is further than the entire trip so far, 900 million miles from Saturn to Uranus. The solar system is big.
In the miniverse, that puts Uranus hundreds of miles down the road, near Kansas City.
Gonna ride that lightning one more time. I'm gonna ride that lightning one more time. I'm gonna ride it one more time, 'cause there ain't no finish line. I'm gonna ride.
Out beyond Saturn, just like on the road through America's heartland, it can look pretty empty. Gives you a lot of time to think and look.
When I was a fighter pilot flying F-18s in the subarctic, I loved to take the airplane up as high as air traffic control would let me. And then I'd engage the autopilot, sort of like I could engage the cruise control in this car. And then I would shut off all the lights in the cockpit so that it was completely dark. And then I would let my eyes adjust. And you could start to see the stars as your eyes opened up. And for me, that was sort of an early taste of what spaceflight was going to be like, as close as I could get to the heavens, but almost no barrier at all between me and the rest of everything else. My first small step into space. If we were making this trip 300 years ago, it would have been in like a horse and carriage, we would have stopped at Saturn, because as far as everybody knew, that was the last planet. It was the furthest planet that we could see with the naked eye.
But there is another planet down that road in front of me. Another giant of gas and ice. Uranus. From a distance, it's hard to imagine the violence going on there. These Midwestern flatlands can get hit by 200-mile-an-hour tornadoes, but if I flew a spaceship into the clouds of Uranus, I'd be fighting winds up to 560 miles an hour. And as you get closer, you start to see something very strange. Uranus is lying on its side.
So if you were the Space Transportation Safety Inspector, you'd look at this and say, what the heck happened here?
Something in the early solar system, possibly some rogue planets, knocked this giant world over, rings and all. And that might not have been the most incredible thing to happen to Uranus. About 4 billion years ago, it was ripped out of its orbit. Gravitational interference from Jupiter and Saturn made Uranus switch places around the Sun with Neptune. That's like Kansas swapping locations with Colorado, but it happened. So today, Neptune is 1 billion miles out from Uranus. which puts the 8th planet in western Colorado. Like the pioneers of old, I've reached the Rocky Mountains. Ahead lies my final frontier. And here's my final co-pilot.
Hello.
Hello.
How you
Commander
doing?
Hadfield, nice to meet you.
It is great to meet Dr. Laura Danley, astronomer and curator of the Griffith Observatory in Los Angeles. Welcome to my spaceship.
Thank you.
We have the privilege of traveling a little bit of the solar system together.
I'm really looking forward to it.
Yes,
We've got a long distance to travel.
Let's
go.
Let's go. Seat belts.
All right.
Engage.
So, Laura, as my spaceship enters into orbit around Neptune, what's the first thing I would notice?
Well, Neptune is blue, and there's nothing you can do.
That'd be a good song, wouldn't it?
That would. Maybe you could sing it later.
Looking down on Earth from the space station, you're struck by the incredible deep blueness of our planet. But the blue on Neptune isn't water. It's reflected light from methane in the atmosphere. And that atmosphere is roiled by the wildest winds in the whole solar system.
There are storms in the atmosphere that appear quite dark.
Like spinning storms?
Yeah, huge cyclones.
Huge cyclones.
And they are so violent that the wind speeds in those are about 1,500 miles an hour.
Like 1,500?
1,500
I mean,
miles
a
an hour.
category, whatever, hurricane, 200 miles an hour is wicked.
Yeah,
on the
this
Earth.
is a category 25. It's
Wow.
way up there.
How big is the storm?
The big one is about the size of the whole Earth. You could fit a whole Earth in it. Yeah, it makes our storms look like kindergarten over here.
Earth-sized storms with winds 10 times faster than my top speed.
Wow, that's incredible.
Yes.
And look at that.
Well, here we are. Wow. What an amazing sight.
An astronaut visiting Neptune wouldn't want to leave orbit because there's nowhere to stand and plant your flag.
No, you can't be standing on it because it's gas mainly.
Sure.
So you would keep falling on through.
Whoa! Here's some solid ground. Neptune's largest moon, Triton.
Wow.
Triton is an amazing world. First of all, it's about 1,500 miles across.
Standing on Triton, what do I see? What's it look like?
Well, an icy surface everywhere. Mainly nitrogen, little methane, maybe a little CO2. If you're standing in the right place, you might also see kind of an orangey, rust-colored coating on it. These are hydrocarbons or organic molecules like methane and ethane that have been singed by ultraviolet light from the sun, and they fall down onto the surface like just a fine veneer on top. And if you were in the right place, then you may see a geyser of nitrogen ice spewing into space.
An ice geyser spewing up around me, wow.
5 miles tall. Think about that compared to, say, Old Faithful.
Miles high.
Right.
Well, I want to go.
It's an amazing world.
Sounds like it'd be worth the trip.
Yeah.
Triton may have something special that makes it a target for future explorers. A warm subsurface ocean with the possibility of life. Think how amazing it would be to gaze from a scenic overlook on a distant world and see someone or something looking back at you.
You ready to pick up speed?
Yep, you bet. How many Gs do you pull in the shuttle?
Not very many, 3. Shuttle's pretty low G vehicle.
Think you can get us 3G?
Sure can. Warp factor 3.
So when you go beyond Neptune, is it like in Star Trek where there's all those things whizzing by, or is it empty?
It's for all intents and purposes empty. Lots of space.
So space is the right name.
Yes, it is. Lots of it. Space, comma, lots of it.
That pile of rubble.
I know.
It's like a Star Trek set, doesn't it?
It does.
Fighting the Gorn.
Why does everybody know about fighting the Gorn? That is like one of those memorable... The Gorn was such a wonderful monster.
From Earth, even the Hubble telescope can barely make Pluto out. That's because it's an average of 3.6 billion miles away.
If you were able to fly out there in the shuttle, it would take you about 20 years.
A long time with 7 people sharing one toilet. That'd be a while.
And then if we were driving at 60 miles an hour, it would take us 6,700 years to get out there.
Wow.
So, yeah.
Are we there yet?
In 2006, while I was working at the Johnson Space Center, my NASA colleagues launched the New Horizons probe to get a closer look at Pluto. But while New Horizons was en route, Pluto was demoted from 9th planet to dwarf planet.
I kind of feel bad for Pluto. You know, it was part of the club for all that time, and we just kind of threw it out just because we changed our own standards. How do you feel?
I have to say, I feel the same, which is why sometimes I mistakenly still call it a planet. It's just a force of habit, and it has a history.
In the summer of 2015, I was on the edge of my seat as the New Horizons probe sent back one mind-blowing picture after another. Suddenly, I could imagine myself walking on this distant world.
I think everyone thought it was just going to be an icy chunk out there.
Yeah, like an ice cube.
Yeah, surpassed everyone's wildest imagination.
Turns out, if I went to Pluto, I'd find a world with a super thin atmosphere that, like Earth's, is mostly nitrogen. A world with mountains of solid ice, 11,000 feet high. And Pluto has an ice field about 1,000 miles across in the shape of a heart. And deep under its icy surface, a huge, warm, liquid ocean. Nobody thought we'd be following the water to Pluto. We're...
Cool car.
Very cool.
There's a mist rolling in from the Pacific Ocean, which gives me a very slight idea of what a day on Pluto would be like.
40 times farther away from the sun than the Earth.
So the sun shrunk down to almost nothing.
Shrunk down to just a bright star.
Really?
So it's not entirely dark, though. Sort of like it is around dusk here on Earth.
So where should we land? Should we land right in the middle of the heart?
You know, that wouldn't be a bad place to land because it's wide open.
You'd have a nice little smooth spot.
Yeah.
Good for skating.
I was just going to say, you're Canadian. Strap on your skates and head on out.
What sort of gravity does Pluto have?
It's just about 1/15.
1/15?
Of Earth's, and the moon is 1/6.
So
you could really jump high.
If you weigh 200 pounds on Earth, you're weighing like 12 pounds on Pluto.
Yeah.
Wow. Be pretty cool.
It would be very cool.
Actually, it'd be pretty cold.
Every day, we're closer to the time an astronaut from Earth looks out from the porthole of a spacecraft and sees...
There it is, at long last.
Long voyage. Imagine having that in front of your naked eyes.
Still can't get over it has a heart on it.
It's just so poetically perfect.
It is, it really is. It's a beautiful world.
And you know, to have been around the world so many times, you look at the world a lot, but it's when you turn and look what there's still on the other side, what's...
Bye.